Hi everyone, I'm Meng Zhou. I'm a fourth-year graduate student from Tsinghua University. Today, I'm very glad to have this opportunity to introduce our new semi-numerical method here. It is developed to simulate cosmic reionization and IgM heating. Our code does not apply the popular excursion set models. We approximate the full radial transfer of UV and X-ray photons with one-dimensional radial transfer and linear perturbation theory. We also use shear window functions to unrun our algorithm rapidly. As we know, for now we're still not able to perform large surveys to obtain 21 cm data from the epoch of reionization. Simulations remain our only choice if we need large amounts of mock data for relevant researches, such as statistical measurements analysis, parameter constraint, and etc. Generally speaking, we can divide all kinds of simulations into two categories. One is full numerical simulations, which are accurate but slow as they are based on full radial transfer. The other one is semi-numerical simulations, which are fast but inaccurate as they adopt some assumptions to avoid full radial transfer. Most of them also don't have an explicit source models. If you need large amounts of data, the semi-numerical one seems to be your choice. And if you compare these two figures from full numerical and semi-numerical simulations on the right part, you can see on the large scales, they are very similar, but if you look at details, they still have some differences. Here we introduce a new semi-numerical method, which is not based on the popular excursion set models, and partially based on the radial transfer, and be flexible to source models. It can be an independent choice for relevant researchers. The algorithm of our code is similar to a classic joke. How to put an elephant into a refrigerator? You need to first open the door of the refrigerator and to put the elephant inside and finally close the door. Here, elephant refers to the photons, and the refrigerator refers to the profiles for ionized bubbles. If you have some three-dimensional realizations of ionized fractions at some time step, we first extract its corresponding one-dimensional profiles. That's like opening the door of the refrigerator. Then we add photons to evolve these profiles to next time step. And this is like you're putting the elephant inside. Finally, we have to print the updated profiles back to some three-dimensional realization. And this is like you closing the door. In next several slides, I will briefly introduce how we perform these three operations. Let's first look at the evolve operation. If we know the profiles at last time step, how can we get the profiles at next time step? And here we use one-dimensional radial transfer, which was developed by Thomas et al. In 2008. They treat ionized bubbles as spherical ones and just evolve them along radial direction. Furthermore, the information we need to evolve these profiles is actually very limited. We only need the central emissivity in the UV band, which contributes the most for ionization, column density, or the ionization rate from X-ray in the first shell, calculated by linear perturbation theory, which I will talk about later. And of course, the local ionized fraction, local matter density, and the gas temperature. The final output is just the updated ionized fraction. In other words, one can think about it as a black box problem with 5 inputs and 1 output. With enough pre-calculated table of one-dimensional radial transfer simulation, we can use linear interpolation to implement these black box problems, so we don't actually need to run the radial transfer simulation here. Then let's talk about how to extract or print one-dimensional profiles from or to three-dimensional realizations. We use shear window functions to do these two operations. The definition is quite intuitive. If some field point is inside some given shell, then we assign it with some value. Otherwise, it's 0. The print operation is simple. We just sum the convolution between one-dimensional profiles and different shell window functions. The inverse one, the extract operation, is a little bit complicated. We need to convolve three-dimensional realizations with different window functions first, and then solve the linear equations with the convolution results as their coefficients. Our code can also involve IGM heating history. We adopt linear perturbation theory, which was developed by Zhang et al. In 2007 to estimate the heating and ionization rate from X-ray photons. The linear perturbation divides source terms as three parts: the spatial average of source, the perturbation of source fluctuation, and the effective perturbation from absorption fluctuation, and then they attenuate them with average optical depths. If we add on cooling rate from different channels, we can get an IGM heating histories intuitively. We perform several tests. The first one is single source test. We put a single source in a statistical universe and expanding universe. Both of these cases have analytical solutions, and we find that our results are roughly consistent with analytical solutions. Then we calculate the ratio of photon budget and ionization numbers per time step and integrate it with different times. We find that if we do not take account of secondary reionization from fast electrons, the ratio of the photon budget and ionization number is very close to 1. We only have around 1% error, which is very consistent with photon conservation. We also test our algorithms in a cosmological density field and find that we can successfully build a two-phased IgM, either neutron or ionized. The global history of ionization and heating are also consistent. So from the global history of ionization, we find that the CMB optical depth is around 0.0515, which is consistent with Planck 18 results. The heating histories also has similar features consistent with other simulations and theoretical predictions. You can see the spring temperature is coupled to CMB temperature at first, and then it coupled to gas temperature later. And at the end of reinizations, both of them will be much larger than CMB temperature. And here are the take-home messages. We introduce a new semi-numerical method that can generate ionization fraction and gas temperature fields based on given density fields and source models. We use one-dimensional radial transfer and linear perturbation to approximate the radial transfer of UV and X-ray photons. We use shell window functions to extract and print profiles from or to three-dimensional realizations. Our code can yield consistent results both in single source tests and in the ionization and in the cosmological density fields. Okay, that's all. Thank you.